Euclidean space ini apa namanya sudah dikenal jauh sebelum Masehi, Oke. Kemudian untuk matriks norm kita bedakan dengan dua garis di sini untuk matriks E. Maka melihat matriks norm adalah maksimum daripada pengalian satu matriks dengan kofaktor dan dibagikan dengan kofaktor norm itu sendiri. Maka matriks E itu akan memberikan nilai sebagai square root daripada kuadratik matriks daripada nilai apa namanya cofactor itu sendiri. Oke, kemudian saya masuk ke feedback control untuk orang di kontrol mudah-mudahan ini paham adalah satu sistem yang umum di dalam kontrol dan di sini kita akan melihat beberapa nilai sensitivity function yang terutamanya adalah nilai sensitivity function di mana memiliki nilai 1 divided by 1 plus EC. Oke, di mana nilai D dan N di sini adalah disturbance dan white noise untuk sistem P dan controller harus meminimaliskan efek daripada white noise. Berbicara kepada H infinity tidak lain dan tidak bukan adalah kita berbicara kepada Geoffrey-Hardy. Geoffrey-Hardy adalah satu mathematician di Inggris, di UK. Dia mendefinisikan satu H infinity atau function infinity sebagai definisi satu di dalam ini adalah mengambil nilai supremum antara satu di dalam satu unit disk supremum itu. Unit disk what I mean is a circle with one radius. Kemudian kita memiliki integration dari 0 hingga 2 pi, maknanya the full circle, kemudian mengambil satu function seperti ini. Maka daripada Hardy ini, beberapa mathematician mencoba memahami fungsi daripada Hardy dan dibawa kepada proses kontrol. Untuk fungsi apa namanya norm 2 ataupun sama dengan Frobenius norm, maka persamaan 3 ini sama dengan maksudnya dengan Frobenius norm, di mana quadratic function seperti yang kita lihat tadi adalah didefinisikan sebagai pengalian antara conjugate transpose with the system, with the function before the conjugation. Okay, and apa meaning of H infinity? H infinity has a feasible measurement. For example, when we have H infinity, it is equal to maximum over all frequency of omega over the transfer function when we have transfer function G omega. Okay, G J omega itu adalah tak lain dan tidak bukan adalah supremum daripada eigenvalue daripada matriks GS. Okay, daripada eigenvalue dari matriks G omega, di mana nanti omeganya itu kita batasi tidak infinity, tidak negatif infinity dan tidak infinity. So kita lihat misalnya satu sistem J omega, kita memiliki input Vt dan output X of t in intensity scalar white noise. Kemudian kita memiliki spectral intensity adalah 1, maka jika fungsi ft kita ambil dalam bentuk sine wave, maka di sini apa namanya the output daripada sistem itu akan memiliki nilai amplitude yang sebesar 2 kali omega dikalikan dengan ini menjadikan dia seperti ini. Nah, di sini nanti kita akan melihat di mana letak maksimumnya dengan menggunakan H infinity norm itu sendiri. Kemudian ada experimental measurement. Maksudnya adalah itu adalah maksimum root mean square value daripada X untuk semua possible input dengan nilai root mean square sampai 1. Maksudnya di sini kita ada input, ada output. Jadi antara input dan output ini kita memiliki maksimum root mean square, untuk semua kemungkinan input di dalam ini. Jadi operatornya kita bisa menulis semua maksimum itu di dalam bentuk supremum untuk faktor norm 2 dan norm 2 untuk ini menjadi H infinity kepada G infinity. Itu maksud dia. Kemudian untuk energy measurement, apa maksud energi di sini adalah kita dalam hal ini meminimaliskan kinetic energy untuk pergerakan satu kontrol input kepada kontrol output yang lain. Oke, jadi di sini X infinity ini kita mendefinisikan seperti supremum ini antara batasan satu sistem dari infinity kepada infinity. Kemudian kita bisa melihat dari definisi ini persamaan 5 menjadi satu definisi kepada persamaan 6, dan kita melihat H infinity atau G infinity ini adalah membandingkan antara output energi dengan input energi. Di dalam hal ini energi kinetic energy buat kita maksud. Oke. Kemudian seperti yang kita jelaskan tadi, bagaimana kita membawa itu kepada design controller. Design controller di dalam hal ini, kalau kita memiliki P sebagai proses atau sebagai plan that we want to control, dan kemudian kita mendefinisikan we have a delta as our uncertain of the function of the plan, uncertain of the plan, kemudian we should design the controller. We should design the controller. From here, then if we rearrange gambar yang sebelah kiri ini menjadi gambar sebelah kanan, maka we will see that we have the bound for uncertainty is less than L. Then kemudian here all the uncertainty yang delta ini kita bisa namakan dengan any perturbation. Okay? Ini perturbation yang kita boleh define seperti apa saja yang dinamakan dengan perturbation. Kemudian general perturbation model. Kemudian dari sini kita lihat general perturbation model. Setelah dari persamaan tadi kita ambil closed loop-nya, dan kita melihat seperti ini memiliki general perturbation model. Kemudian delta T, by ignoring delta T, we have the function F sendiri menjadi seperti ini. Ini yang kita namakan nanti sensitivity function seperti yang saya maksudkan sebelumnya. Jadi sensitivity function ini adalah sensitivity function yang menjadi objek daripada designing the controller. Kemudian kalau ini kita lihat secara H infinity, maka batasannya upper bound of this function adalah 1/n, seperti yang kita define daripada delta uncertainty itu sendiri. Ini bisa dilihat pada artikel yang ditulis oleh James. Oke, nanti in the last talk saya punya list of the article. Oke, maksudnya di sini juga sekarang objektif kita adalah untuk mendapatkan compensator C such that makes the closed loop system stable and minimize the peak value of sensitivity function. Sensitivity function adalah yang ini nanti, the inverse of this sensitivity function. Jadi sensitivity function value kalau kita lihat untuk persamaan ini akan menjadi seperti ini. Ini akan terlihat untuk semua omega atau semua frekuensi, okay? Dari low frequency to the high frequency, and you have this sensitivity function. So kita nanti di dalam closed loop design kita melihat sensitivity function itu we have to minimize. So saya lihat beberapa publication untuk H infinity. H infinity start daripada tahun 70-an hingga sekarang, maka ini untuk sekarang trend publication on H infinity is very high, sampai 6,000 artikel in a year, in the last 2-3 years, sampai 6,000 artikel publication for H infinity. Okay, now how we can bring the H infinity to optimal control framework? Okay, sebelumnya kita definisikan dulu satu proses atau plan kita. We have exogenous input. Okay, we call this is W, and kita punya aktuator, kita sebutkan U, dan kita punya regulated output dan sense output. Sensed output adalah yang kita maksud, yang kita bisa ukur. Sementara this regulated output menjadi satu hal yang lain. Di sini saya definisikan, okay, output to be controlled and minimized adalah Z, and output used by the controller. Jadi ada dua output, satu output yang kita kirim ke controller, and satu output yang kita minimizekan. Okay, dan ada input W, itu dalam bentuk disturbance, tracking signal atau apa saja yang bentuk disturbance. Kemudian kita namakan dengan exogenous input. Kemudian ada U sebagai output daripada controller. Jadi controller mendapat informasi dari Y, kemudian memberikan input U kepada controller. So now kita bisa definisikan dari dari persamaan ini menjadi seperti ini. Oke, kita memiliki input disturbance dan output disturbance here. Kemudian controller has to minimize the Z. Okay, the Z here daripada controller seperti ini. Dan for the linear system P, kalau kita punya linear system dengan 4 subsystem, we call P11, P12, P21, and P22. And if we see this by algebraic equation, we will have this equation. Now, you can see the mapping of P11. It is from W to Z, and P12 is from U to Z, while P21 and P22 is from W and U to Y. This is the mapping, and the mapping is written here for the MIMO case. And now the closed loop from here, when we have the plan like this, okay, now the closed loop will look like this when we have the P, okay, because we define P11 as our overall, and then when we see that P11 will be A, and P12 will be B1 and B2, and P21 will be C1 and C2, and P22 will be the D11 and D12 from this. Okay, jadi we can see the different from that definition. Now, while we do the control loop, let's say we have the control law U equal to K multiplied by Y, the output of this, and where K is our controller we need to tune or we need to find out, and we define the K to be A sub K, B sub K, and C sub K. Okay, and then from here we have the Z. Okay, P11 W, and we have this from the previous system. Then we have U like this. Now, if we replace U, okay, we replace U by this U, okay, by this U, then we will have, okay, like this, and we have like this. Okay, now we can replace the U to make the same like this. Okay, we make this U to the right, and then we will have something like this. When we have something like this, now you see that the U has the sensitivity function again, 1 minus Kp22 and multiplied by Kpc. So in common right hand, we have what we call PC over 1 plus PC in simple feedback loop. Now you have this U also in the sense of sensitivity function. Now we solve the Z function. Before we solve this for the U, now we solve this for the Z. When we solve for the Z, you have something like this. From here, you can see we have lower linear fraction transformation and upper linear fraction transformation. What we mean by lower mean we have the feedback Y to the controller and output U to the plant. And upper one is we feedback the Z and we send W to the plant. Okay, and the sensitivity function for lower bound is this, lower LF, linear fraction is this, and the upper linear fraction is this. Okay, and from here we have this definition now. We have X. Now you have this is the common definition in any H infinity controller. We have X dot. What I mean is the dynamic of this equation, and then we have the dynamics also for Z and for Y like this. Okay, this is for the lower linear fraction system. It is well posed. Okay, it is well posed for this kind of the controller. And now our job is to find what will be A sub K, B sub K, C sub K, and D sub K, and then we can have the controller is here. Okay, and if this one is we represent in a state space representation of this closed loop system, then interconnection is well posed. What we mean well posed, we can solve by algebraic later on. Now we can represent this in terms of state space. When we represent this in terms of the state space, now you see you have only a single differential equation with in the matrix form. We have dynamic of the plant and also dynamic of the controller. We call this dynamic of the controller, and from this we can find what is the U and what is the Y of T from this control. Now from here, now we have this problem. Okay, we have this. Okay, when what we call this well posed. When we have this well posed, we have this one is defined to be from this one. Okay, from this we define. We have this one now. Okay, we have this one, and this is the interconnection is well posed if and only if the matrix, this matrix is we can invert. This means invertible. The inverse of this matrix will be this kind of the invertation. Invertible. So what does this mean? That this matrix must be invertible in this kind. Okay, then we can find what is U of T and Y of T at the same time. And we can say that this is well posed if and only if the matrix, this matrix is invertible. This matrix is invertible because the rest is not invertible. It's only for lambda. Lambda is invertible. So this means that this one is invertible. And here I mentioned for D22 dk and also equivalent to 1 minus dk D22 is mean for upper LFT function, lower fraction function. And then it is sufficient condition to see that dk equal to 0 and D22 equal to 0 to see this invertible. Over okay, we need to enforce this constraint then. Okay, kemudian kita bisa lihat to solve for dk equal to identity and D2 equal to 0. This is used for audio effect or Larsen effect. Misal, for example, kalau effect daripada mikrofon balik, maka we can define dk and D22 to be identity matrix. So then will be the 0. So then from this interpretation for the lower linear fraction, we have this all we call as A matrix. This we call the gain matrix, and this is the gain matrix for the output, and then this is output gain matrix. And we have this as the presentation in the state space equation now. So from here, now we can use this definition of optimal control H infinity problem is said that the minimum to get K in sense of H infinity, it is to have the H infinity bond for lower linear fraction that is equal at the L norm atau second H infinity norm. Kemudian what is H2 control problem? It is such that when you have this is belong to H infinity. So then if you want to solve by direct calculation by this H infinity, quite difficult. And now when we choose the K, we choose the K such that we can minimize this sensitivity function instead of H infinity. Instead of H infinity mean we minimize the maximum value or the supremum I mentioned before. We have to minimize that supremum. Then this is equivalently to see that when we choose this, we want to minimize of the controller, it is mean that we are minimizing the whole H infinity of this vector, of these matrices. Then in this case, the problem is non-linear. Why? Because here we have a non-linear case and we have non-linear case. So we can linearize this equation by using Euler parameterization or coprime factorization. But I don't want to go to that now. I want to go to solve this problem by using linear matrix inequality. So we can also specific for the case of static full state feedback, also change of the variable and also change of variable in dynamic input. There are several ways. For example, for this non-linearity problem, we can define such that this sensitivity function as the R, okay, as the R, because this is high non-linear, and then we can minimize the system to be like this minimization now, where we choose the R to minimize this sensitivity function. Now, from this non-linear, now we have a linear, but somehow the K later on, the gain matrix for the controller has to be calculated to be like this. While you have R, okay, well, you calculate the R from this one, we choose the R, we minimize this one from the R, then we have there, we can calculate back to K to find the K. And how to minimize this H infinity? This is the problem here because it's not that easy. And how controller stable if this exists? How does it exist? If we can have this inferred of this function, and it is a bonded linear operator, and which space we can use, how we can go by that. Maybe we can go with Banach space and so on. And an important brand of this control later on, we can use coprime factorization and Euler parameterization. But I don't go to that part, okay, on Euler and coprime factorization, but I go to how to represent this in H infinity control by using linear matrix inequality. So I come back to this. Let we define from this previous function, we define f, okay, as u of t equal to f of x, okay, then we call u is equal qi, and k itself is belong to be this now. Now you can see that. Now this will be the same with what you have. Yes, okay. We have k is like this, and now we can have the same plan what we have before, but now we have this kind of p. Now by using Kalman-Yakubich-Popov lemma, then when we have this kind of transfer function, okay, transfer function in terms of matrix, then it is said that it is less than gamma. When we calculate the H infinity norm of this Popov lemma or Kalman lemma, this less than infinity norm. It is now from this one, it is somehow equivalently will be this type of the equation from where this I got this equation is coming again from the definition. I will come with the definition later on. Okay, with this Kalman and Popov equation. It's nothing else. It is in sense of Lyapunov. This is give us the Lyapunov function later on. Okay, then according to lower fraction system, we have this definition. Okay, and then by applying the Kalman lemma, that is less than gamma, if then only if x is p positive, strictly positive, then you have this kind of matrix multiplied by this matrix now from here. Okay, and this matrix here I didn't write. That mean is similar. I mean the conjugate of this matrix, the conjugate of PB1 of the matrix. It is a non-linear matrix inequality again. So recall a square complement. What I mean here, linear matrix inequality. So here P is unknown, F is unknown. P unknown, F is unknown. So two unknown there. Then when you have two unknown together, you cannot solve to get the unknown one. So we can use Schur complement. Here the Schur complement. Suppose we have this matrix. Okay, so we have this matrix. We call sigma matrix. Then this will be presented for this is positive if and only if gamma is positive, and this give us the lambda minus theta and inverse of gamma, and it is positive. And it is also similar. If this gamma is positive, then the sigma is also positive if and only if this given us this 0. Now, how we can use this definition? Okay, how we can use the definition to the previous problem here, to the previous problem to separate between P and F. Now we can use this one. Okay, now I write here we have gamma, here we have theta, and here we have sorry, this is the lambda and this is the gamma inverse, and we have this as the transfer. Okay, now we can represent this kind of matrices will be in terms of linear matrix inequality. Okay, now from here we can bring to this problem. Now this problem is somehow look like this, okay, for the closed loop system. Now, again, by using this B linear and P and F, I mean the non-linearity, which sometimes we call B linear, and this will be exist if then only if we use this Schur complement, you will have something look like this. So then from here, again, is this about the dual of Kalman? Same thing, so I don't want to go on that. And the condition, if we multiple both condition of Euler for the, I mean the proof, it is then you have this to be this. Okay. Then from that, by on the theorem 1, we can use the following equivalent of F such that this is what we have before on the lower bound of linear fraction transformation, and this should be less than gamma. And it is now you can represent this equation in terms of the linear matrix inequality. Somehow now you see that the unknown y and z is represent in z, no more f and p there. Okay, and here it is already linear. And then from this one, you can find out what is F unknown by using this equation later on. When you calculate, you got Z, and you know Y from the also from this you can find the Y, and here you can find the F. Okay, from there for the lower bound again, it is now equivalent to this problem what I have before. This equivalent with this now. Okay, equivalent with this. So instead of solving this by H infinity norm, bond, we can also solve by using linear matrix inequality. So now I give you the function in MATLAB, how you can solve linear function inequality. So we have this kind of system. I wrote this in MATLAB in LaTeX code, and we have these n as the size of A, m as the size of B1, and O as the size of B2. And then you set the LMI, and then after you set the LMI, you define unknown variable mean. We are defining the decision variable Y and Z, and also gamma here, because gamma is unknown. And from here, we try to minimize the gamma. We use these the entry of the matrix to mention about A, Y plus YA by using this matrix. This is for the entry 1, 1 of the matrix. Matrix 1, entry 1, 1, and Y unknown, and this is you know, and this you know, and this you make symmetrics. And this is same thing, this unknown, this is you multiply by B2 multiplied by Z and 1, and you have something like this in lab. And for B1, this 0 is here 0, okay, and so on. And then negative Z is here to represent the transpose, and you have this gamma, okay, and you continue that, and then you can get a loop to get the minimum gamma from here, the minimum gamma. Okay, from that you can calculate what is Y, and then what is Z, and then you can calculate what is F accordingly to the and for this optimal Y and Z. And I go now with time delay. I don't want to go, take a long time. For time delay system, and this is the publication of a time delay system. It is more than 60,000 articles published in the year 2019, something like this. This is very big publication on this time delay. And why time delay? For example, when we go to shower, we have hot and cool system. So somehow then I would like to say play like this. When you have to turn on the cool, you have feel the cool in your system, in your skin, and then you turn off the hot. When you turn off the hot, then you play the school. You feel hot, and then you turn on the spool only. So it's always between hot and cool until you find the adjustment. And it is a delay in between mixing until reaching the head. Okay, until reaching the head. So then also time delays happen in many when we call in system, when we have the input like this from the controller. Controller will produce at time t a u, but it is implemented to the plan after some time. And it is usually varying time here. And also the output from the plan is also given at yt and receive it by the controller at yt, at some time delay, and also varying, and we call this tau2. And now when we use cable like this, communication through cable, the delay can be minimized in communication. But somehow more lately, the application of these cable is cut off to be using Wi-Fi or radio communication. And in this radio communication, the delay is huge. Huge. All can be in delay, and also having a varying delay. And nowadays in remote communication, like we are doing now in using this Zoom application, we cannot avoid from the delay, and this delay must be compensated in the controller design. And also in military proving or remote communication for the military equipment, there is also delay to the command center, from communication in the field to the command center. So that's why the delay. And now, if I define the controller like this, we have, the dynamic of the system with this delay. I go with first, the delay is fixed, it is not varying, and then we have this one, and this W we call the disturbance, and U is the input signal, and this is another U input delay, okay? And similar for the measurement, we have a delay also. And then if we have U of T, I mean our control signal from X of T, then we can have the feedback loop is something like this. Okay, we have the feedback loop something like. Now from this transfer function, we have Wt to the output Yt. We can represent in the Laplace transform, okay, in Laplace transform to be like this. Now we can find the K such that this minimize the H infinity norm that is less than alpha, less than gamma. For the gamma is positive. For the gamma is positive. So this definition now, okay, it is similar or equivalently, we can represent by this definition, okay, by this definition. We have the integration from 0 to infinity of the output in sense of quadratic, minimum subtracts or different between the disturbance. So you see that we try to minimize this disturbance with the output, with the wake of gamma then, okay, for the whole time from 0 to the infinity. And this is, we can represent for the whole disturbance there in terms of L2 norm, which is bonded from 0 to infinity. Now we can rewrite it, this term as this term now. Okay, we write it this as this term. Okay, this we integrate to dt. We integrate to dt. Now we choose this Lyapunov-Krauskowski function. We have this x, I mean this Lyapunov, and this is to deal with the delay in the state, and this is to deal with the delay in the input. Now for all P, Q1 and Q2 must be positive. Then if we take the derivative of this Lyapunov function, we will have something like this. Okay, from this one, we can represent now in terms of matrix. We will have this, the derivative function from matrix like this. Now, we have to include the H infinity norm for this matrix, for this Lyapunov function, is by adding this equation. Now we have the performance index from 0 to infinity. We have this different, okay, input, output and input different, and the Lyapunov function here. And we take this, and then we have to have the gamma positive. And this they give the wake matrix as this one. Now from this one, we can have now to be this. Well, I have here psi I and psi I transpose. So this psi is this guy now. Okay, we have this as the matrix is what we have from here. After we do this, because this means this one you add by the previous one here. I have this one and this one. Okay, from here now you have this one. After you add this, you can have this matrices now. After you do the what I call Schur complement. After you do the Schur complement, you have this one. Okay, so you have from here, and then if you multiple both sides by y, what is y is inverse of the p, then you have this kind of the controller. You have of this kind of controller. Okay, and you have here as this controller. Then you have x. Here I have let xk multiplied by y. To eliminate the b linear, we have y multiplied by k, or k multiplied by y, and then another q here. This one is also b linear, and this is also b linear, and then we can eliminate this b linear by this type of matrices now. So now you have a linear system. Okay, you have a linear system. linear metric inequality. So we can solve this linear metric inequality. The code example I gave it before, and to make sure that these matrices is positive. And you can calculate the control again then by having x multiplied by inverse of y. Okay, and now I go to delay dependent. This is before I call delay independent. It's not put delay, not depend on delay itself. When I have delay dependent system, so I define, is define the delay now for time varying delay, but I have in the bound from L to H. It is L is greater than or equal to 0 and H is greater than 0 for sure, and D1 and D2 the derivative of the delay function itself. And from here, first of all, I choose L equal to 0, and from this L equal to 0, we let the Lyapunov function to be this, and for sure that P is positive, Q is positive, and R is positive. Okay, positive definite function. And from here we calculate the derivative of this function. From this derivative, we calculate along the trajectory 18 from assuming that B1 equal to B2 equal to 0, meaning there is autonomous system without controller and also without disturbance. From here we have this function. Okay, we have these psi transpose omega and psi. What is psi? X, and X subtract by this the state of delay state, and the delay state subtract by this integration, while omega itself is this one now. Okay, omega itself is this one. And now the problem in hand is to solve this problem, this integration. So this integration term we can solve by using Leibniz-Newton formula, or we can solve by Jensen or Wirtgen integral inequality. We can solve by free matrix based integral inequality, also Bessel-Legendre inequality, or reciprocal convex approach. Okay, I will go with reciprocal convex approach only because nowadays I'm developing this theory on reciprocal convex inequality approach. So suppose you have this integration, and this integration is somehow we can first see that there is a derivative. I mean, this integration bond we can break to be two parts, from x of t to be x minus dt, and dt to the h of t. So mean we divide it to be two parts, and this division will be like this. Okay. And from here, this is the upper bound by using reciprocal approach. And then this one, we can simplify of 1 over the function of delay function by having another matrix, what we call W matrix. And then from W matrix, we can eliminate this delay function. And from here, then we can separate the variable of x t and x t subtract by dt and also x t minus h, and then we can have like this the function. So this integration now, okay, this integration now has the upper bound like this, So we can replace this equation. Okay, we can replace this integration by these matrices now. Now we have this kind of the matrix. Now you see it is already linear, and we can solve for unknown P, Q, and R, and also W. And you know that P must be positive, Q must be positive, R must be positive, while W can be anything, can be positive, can be negative. So, and also ensure that this bond must be positive for R, W, and R must be positive. Now, for the case when B1 and not equal to 0 and B2 not equal to 0, and we have the output, the control law like this, ut equal to kx of t, then the derivative of LKF if give us this kind of the function. But now you have, I simplify this kind of the function. Now we can solve this one in terms of along the trajectory. We have x dot here, then x dot this we can represent by this. We have 2x this transpose t multiplied by p, and this is the trajectory. Okay, when we have b1 not equal to 0 and b2 not equal to 0. And same thing for solving this one. Okay, same thing from solving this one. This one I can represent now how you can solve for this along this trajectory. We have h r like this, okay, and another this one. Okay, we can write like this. And now we have the fulfillment index like this again, similar to like before. Then from here you can have the linear matrix inequalities like this. Okay, now you have p and k at the same time here, p and k at the same time, and we can do by multiplying this matrices, the diagonal matrix of y, iiz, to the left and to the right of these matrices. Then we can have taking the z as r infinity and x equal to ky, and this bar q and bar r and bar w, and also head of w. Then we can have this kind of the matrices, and we can solve these matrices by using our compact optimization, and ensure that all these matrices, for this one will be negative, this will be positive, y positive, in this also positive, r is also positive, z positive, and also gamma is positive, and we can calculate the k as equal to x multiplied by the inverse of y. And in terms of time varying delay, before I go with delay dependent, and I go with time varying delay. Time varying delay, now we have the non-bond, same non-bond like this, but now we have more complicated. We should have, this QF function, the Lyapunov function. We have P1 and P2. P1 is this Lyapunov function. Now it's quite long Lyapunov function, and ensure that P is positive, QI is positive, RI is positive, and also SI positive, and TI positive, and UI is also positive. And Lyapunov function number 2 is this. Okay, it's also long with double integration. And then for the case when m equal to 2, for the case when m equal to 2, we have, I make it short, not for the whole thing. And you have this kind of the matrices. Okay, you have this kind of matrices after you do that. And ensure that this is also positive. Then how we can implement that matrix? Okay, we can implement like this. We have the plan. Okay, the plan have the output in terms of y. Y we can feedback to compare with our reference, and we can implement the integral action on this term, and the state feedback will be here. The state feedback will be here. Okay, and the key what we calculate is here, and this is the key I from the PID controller. So I explain application for diabetes system. So the diabetes system has 2 delay. The first delay is the production of glucose from liver, and the second delay is the production of insulin from the pancreas. We have 2 delay. Okay, and this all how the what we call feedback loop model of glucose insulin system in our body. Okay, and from here we have this kind of equation. This equation is quite simple. Only 2 equations. It's dynamic for glucose and dynamic for insulin. Okay, by applying delay, and here the defined delay by most of model developer is not in varying delay, but in the real time, tau1 and tau2 is in the real application to 1 and to 2 is varying delay. Okay, we have function 1, function 2, function 3, function 4, and function 5 is all non-linear except the function 3 will be linear. So from here you can see that function 1, function 2, function 4, and function 5, it is how behavior of that system. Now, from this non-linear equation, we linearize to be this. Okay, we linearize the equation as what we see before. We have A0. Now A0 is this matrices, and A1 is this matrices, and A2 is this matrix, and we have B is this matrices, and BW this matrices, and we have defined psi1 and psi2 as the exercise term. Okay, I come back to here. This gamma, okay, this gamma is the exercise term. Okay, this exercise term. Not the same with the gamma in the controller. This gamma, the gamma cell in the pancreas system. Okay, and this gives us how the absorption of glucose by the exercise. For more detail about this model, you can refer to this application. I mean article. So I implement this in Simulink. It's like this. It's look like this. I have a dynamic model here, and this dynamic model I have the input with integral action here, and the control gain. What I calculate, I have this controller gain now, and I multiply by this controller gain, and I have this. Okay, the controller gain has the information of the glucose and the information of the insulin. I mean, both state is known in this case. Even one state is unknown, but I assume is both states is known. And from here, I introduce the exercise time and pancreatic beta cell. It is to say that between diabetes type 1 and diabetes type 2, and we have the gamma here. The gamma is the exercise time, it's exercise effect, and we have the derivative. I mean the two here, to 1 and to 2 is to see this as I mean the delay to the system. Okay, and now from here we have the open loop response. I mean the blood glucose level is behave like this. It is a fluctuation between 75 through 155. The peak is like this. Now we want to control to be inside the normal bond of type 1 diabetes patient. And the meal intakes, what I show meal intake is every, how to say, 3 times a day. 3 times a day, every 8 hours. Every 8 hours we have 1 meal. Okay, we have 1 meal. We eat every 8 hours. And the closed loop response look like this. Now you see from the previous one, I mean open loop is like this. Now the closed loop is look like this. More or less going to be in 120, and where our set variable is there. And mean the controller can handle for this kind of problem. And I forgot to tell you, meal intake is I assume as disturbance function to the modeling here. To the modeling here, this WT is disturbance to the system. And you see, this is how the behavior, it is still, I mean, oscillate there, but the oscillation inside the bond, and it is the insulin injection. And I think that's all what I can deliver the talk for today. If you have any question, I would like to be happy to answer. Okay, thank you so much.
Baik, terima kasih Prof. Syafiie atas paparannya di sini. Jadi memang tadi terlihat cukup rumit ya untuk nanti mendapatkan desain sebuah pengendali dengan berbasis kepada pendekatan edge infinity. Walaupun sebenarnya untuk penerapannya itu sangat mudah. Dan tadi yang gain-nya itu saja kayaknya Prof. Gain-nya static. Itu saja nanti yang perlu diimplementasikan saat kita nanti menerapkannya pada suatu permasalahan real di sini. Terus kemudian yang menarik juga tadi diangkat adalah tentang sistem time delay system di sini. Time delay system secara naturnya itu banyak hadir di proses kontrol terutama. Tapi sekarang dengan dunia yang semakin global, mengarah pada globalisasi, terus ada pendekatan resource sharing di sini, ya, network control system, multi agent, ya. Jadi mau nggak mau itu nanti kita akan berinteraksi dengan agent lain, dan itu perlu ada komunikasi dan nanti akan memunculkan latensi atau time delay. Muncul time delay. Dan tadi menariknya time delay ini bisa ini ya, tidak fix ya, bisa berubah, dan yang ada yang multiple time varying. Baik, kita masuk ke dalam sesi tanya jawab. Kami persilakan buat yang ingin pertama, bisa silakan raise hand, sebut namanya, dan bisa langsung nanti menanyakan. Silakan. Ada yang bertanya? Kalau edge infinity, edge-nya itu apa itu ya, Prof?
Edge-nya, oke. Edge ini adalah nama daripada saintis tadi.
Oh, nama saintis ya?
Ya, itu stand for Hardy.
Hardy, dan Hardy.
H-nya adalah mana dia?
Hardy itu ya?
Ya, Hardy yang foto yang tadi saya sengaja ambil karena itu memang dari beliau.
Dari beliau. Kalau ada tadi L2 itu L-nya?
Itu bukan L, tidak ini, itu linear saja. Tidak bermaksud.
Oh, baik. Silakan, belum ada yang bertanya.
Hardy space ya, dari Hardy space.
Hardis ya. Tadi ada matriks C-nya itu, matriks C-nya itu sebenarnya mengarah ke yang variabel yang dikendalikan atau variabel yang terukur.
Yang mana? Yang itu saya nggak ingat yang mana satu, Pak Aris.
Matriks C di modelnya.
Di model. Itu
model
waktu
sistem.
Saya ngomong,
model sistem yang state space.
Yang awal ya. Saya ngomong yang awal, yang bagian sini.
Sebentar, lupa ini kan ada
Karena banyak C yang saya sebutkan, banyak matriks.
Kan C itu bisa didefinisikan, kita bisa kan kaitannya dengan state variable ya. Kita bisa mengisinya itu merupakan yang variable output yang dikendalikan atau variable yang terukur, kan yang diukur dengan yang dikendalikan bisa berbeda itu kan. C ini yang dibentang ini Z atau Y.
Oke. Mungkin saya boleh paham dari pertanyaan ini. Di dalam ini kan ada dua jenis controller, yang mana yang pertama kita namakan output feedback control, maknanya kita mengambil Y sebagai feedback, atau state feedback control. Ya, jadi yang dimaksud dengan state feedback, kita mengambil state daripada sistem menjadi feedback. Dan ada kalanya problem di state feedback adalah kita tidak bisa mengukur semua state, yang kita hanya bisa mengukur beberapa state. Seperti contoh saya berikan di diabetes tadi, kita bisa mengukur state daripada glukos, but kita tidak bisa mengukur state daripada insulin. Belum ada satu sensor yang bisa mengukur kedua-duanya secara bersamaan. Jadi kalau kita mengaplikasikan state feedback control, kita perlu mendesain satu observer di sini. Observer. Tapi kalau maksud Pak Aris tadi C yang mana ya? Saya banyak menyebut C di sini. Mungkin yang terakhir kalau yang tentang time varying delay, kalau lihat time varying delay, C di sini adalah measurement. Output kepada state itu sendiri. Nah, ini di sini saya sederhanakan, saya tidak menambahkan delay di sini untuk saya menyederhanakan measurement. Boleh dibuat secara general juga untuk mendapatkan delay di dalam measurement itu sendiri. Mungkin ada pertanyaan dari kawan.
Mau bertanya?
Aplikasinya banyak ya. Banyak aplikasi ini di mechanical system, electrical system, di communication, terutama yang remote control, yang low power calculation, itu banyak application H infinity. Seperti saya sebutkan tadi, application di di aircraft, application di rocket, satellite, application di satellite, dan also banyak application lain termasuk di military purpose. Banyak application di military purpose, terutama untuk menghematkan kalkulasi. Karena kalau kita memakai predictive control, kita harus mengkalkulasikan banyak calculation. Ya.
Oh, itu berat itu, Prof. Berat itu. Jadi rasanya ini cocok ya kalau buat S infinity, buat sistem yang kompleks dan dia punya respon yang sangat cepat gitu. Nah, kan berarti butuh komputasi yang simple, yang singkat gitu. Nah, kalau pakai prediktif itu nggak ngejar kayaknya. Buat roket, buat misil itu rasanya pas nih.
Iya.
Baik, ada lagi yang ditanyakan?
Halo, Assalamualaikum.
Waalaikumsalam.
Sorry, I have something to ask, but let me find the place first because I'm driving right now. Baik. Terima kasih.
Boleh.
Okay, nice to meet you, Profesor Syafiie.
Ya.
Oke, saya Idris, salah satu mahasiswa di sini. So, are we going to use Indonesian language or English language?
Bahasa Indonesia boleh. Saya batu cakap saja agak susah dalam bahasa Indonesia karena terminologi banyak in English ya. Okay.
I'm trying to speak very slowly. Oke, Profesor Syafiie, pada saat saya melihat, I'm sorry ya, saya terlambat mengikuti presentasi Anda, tetapi kalau tidak salah melihat, saya lihat pada saat penurunan persamaan infinity control with LMI approach, so that you do the linearized equation, right? Yeah. Jadi Anda melinearisasi beberapa equation in order to implement the LMI approach. Is it right?
Ya, betul. Yes.
Oke. Nah, pertanyaan saya, jika kita melinearize pendekatan ya dari suatu sistem kendali, apakah implementasi H infinity based on LMI approach ini terbatas hanya untuk plan model yang linearized juga atau linear model plan? And can we use this approach for nonlinear system or nonlinear plan model? That is my question.
Okay, good. Tadi saya bagi contoh tadi for this model, This model is non-linear model, and we linearize the model. We linearize this model, and then we tune the controller. We find the controller. From this controller, we apply back to this non-linear model. And this is how the behavior, the non-linear, and this is the response from the non-linear model by applying the linearized, system and tuning based on the linearized system. And it is exists also H infinity controller for non-linear system, and also tuning based on non-linear model. And it is not solving. It is possible to use linear matrix inequality, but it's quite complex and mathematical if I go on that. Very complex on mathematical, and it is difficult to understand. That's why I bring to this preliminary talk on the linear system and linearized model. Okay, I think that's you can do by linearized the model. And to be easy to implement, we can linearize the model around the operating condition, and then from there, your linear model and non-linear model will behave the same around the operating condition, unless you have far away from operating condition. But this H infinity controller is guaranteed for high disturbance system to be stable. There's another thing. Well, even you do by linear system, but it's guaranteed for high disturbance. Okay.
So you mean that even though we are using the linear model,
yeah,
this controller will still behave on the excessive disturbance, right?
Yes.
Okay, but Professor,
reject disturbance. Yes. Sorry.
If you want to implement this control for the non-linear model, how
Yes.
can we reach the stability? Because I saw that in your equation, the stability
Yes.
still needs P matrix, right? Lyapunov
Yes.
P matrix.
Yes.
As we know that Lyapunov matrix will be derived from the B matrix, which is linear models. Because in non-linear model, non-linear equation, we don't have any B matrix.
Okay. So just now, when we talk about Lyapunov function, let I go to the early Lyapunov function. So we are talking this definition, okay, Lyapunov function along the trajectory, and we define that Lyapunov function, for example, this Lyapunov function along that trajectory. And if you see that this trajectory will be non-linear, then you can replace this by non-linear equation. And when you solve to get the P matrix, it's not that easy. Again, it's not that easy. But it is somehow you can use later on with advanced numerical method to solve the P matrix, to solve the P matrix for non-linear Lyapunov function. And it is exists many methods on solving non-linear Lyapunov function. You can refer to Hassan Khalil books, and you can read on how to solve non-linear Lyapunov function, especially. And also now exists machine learning method to solve the Lyapunov function, for unknown matrices there, for unknown matrices, and guarantee the positiveness in the matrices. Okay, maybe I would like to explain. No one asked me why P, Q, and Q1 and Q2 in this case, or all the Lyapunov gain matrix has to be positive. It is because to guarantee that the derivative of the matrices must have a negative effect, negative function. So somehow, if you see about the stability theory from anywhere you are, we want to drive the function to have negative slope in the function. Suppose I can draw. If I have the board, I can explain very well what is meaning of having positiveness in guarantee of the derivative, because the derivative of the function is mean that we are looking for the slope, and the slope of the stability is negative. And to make a negative should have positive in the function, right? Okay.
Prof, I'm sorry, Prof. Actually, I do
Yeah.
understand about why do we need the P matrix of Lyapunov should be positive. But my question is, if you want to find the P matrix, whether it is positive or negative, but if we want to derive or to calculate the P matrix, we still need B matrix, which is it is input matrix for the state space. What I mean is, if you want to find, if you want to implement the this kind of controller for the nonlinear system or nonlinear pan model, how do we find this B matrix or input matrix? Because there is no any B matrix for nonlinear equation. Because we need this B matrix in order to find the P matrix.
Okay. Here the definition of this one. Okay. You mean here we have the derivative of the function, and this is we define a long trajectory, for example, in equation 16, and this x dot x is that trajectory. If it is non-linear, then we have to replace by the non-linear system, and all the equation will be non-linear later on, and you have to solve for non-linear. And about the B matrix, what do you mean by B matrix? Do you mean
matrix input matrix? Yes, correct.
This B matrix.
Yeah,
this
yes,
one.
Correct. Yes, correct.
Yeah. Okay. Even those. Okay. Now, if that B matrix, you mean, okay, if I go back to here, okay, I go back to here, okay. When I define this one, okay, I define this one, and you have this will be, I mean, if your function x dot is having b, I mean having u there inside the function, and it is non-linear, and later on you should have to solve this non-linear problem here. And to solve this non-linear problem, you can apply like co-prime factorization later on. You have to separate again between state and u and input function in the end. You got what I mean?
I get what you mean, but still, what I mean is, I do understand about the linear model, how to solve the Lyapunov P matrix for the linear model, because in linear model we have also B or input matrix, so we can easily calculate the P matrix, right? But for non-linear model, I'm still I was still confused how to calculate or to derive P matrix without B matrix like that one.
First, if it is the system is autonomous, if system autonomous without U, okay, and this one is easy. But when you have U there, and you can also use what we call Lie factorization, and you can separate between U and state. Then from that factorization, you can have the B matrix. You ever heard that terminology?
Yeah, do you mean factorization is we are implementing Taylor series?
No, not Taylor series. Suppose I can write, but I cannot write here. Okay, I will show you. All right, 1 second. I will show you. I mean, you can separate later on. Okay. Suppose I have this non-linear function. Okay. Suppose I have this non-linear function x and u. Okay. Now this one you can approximate by one factorization that you can have this is and you can separate this by another function of this. Sorry, you can separate by u. You can separate this by u.
Yeah.
And then from here, while you separate this, okay, while you separate like this, Okay, then you can see the X, this and this as separate, then your P matrix will be different. I mean, you can separate the B matrix itself. I think if you're interested on nonlinear, we can discuss further for nonlinear case, and when we involve the time varying delay or on that system, and that Lyapunov function will be very, very complicated, involving some triple or even fourth order integration. Sampai 4 kali integration. Sorry. Sampai 4 kali integration. Sorry.
Okay, Prof.
Right.
Maybe you can discuss furthermore later on regarding the nonlinear implementation to the nonlinear model.
Yes,
okay, thank you very much, Prof.
Yeah, you're welcome.
Ya, baik. Jadi nanti kalau mau diskusi lebih lanjut bisa nanti ada sesi tersendiri ya. Mungkin pertanyaan terakhir, ada yang ingin bertanya? Cukup rasanya ya. Cukup rasanya. Baik, Bapak Ibu semua, para mahasiswa, kita akhiri kuliah kita kali ini. Kami ucapkan terima kasih kepada Prof. Syafiie yang sudah bersedia sharing ilmunya ini pada kita semua di sini ya. Ya, ini merupakan satu kalau di sistem kendali itu tidak ada yang metode yang absolut gitu, yang paling superior. Masing-masing punya plus minus, punya kelebihan, punya kekurangannya juga gitu ya, termasuk ini juga, yang termasuk yang lain juga. Jadi tadi sudah disebutkan bahwa kalau yang robust control nih, yang ini sangat mudah untuk diimplementasikan, tapi memang komputasi offline itu yang cukup rumit di sini ya, tapi itu minimal akan membuat saat implementasi kita tidak harus berpikir tentang mikroprosesor yang harus punya clock tinggi nantinya gitu ya. Atau konsumsi energi juga akan lebih rendah. Terima kasih Prof sekali lagi untuk kesediaannya dosen tamu pada sesi kali ini. Kita sama-sama berikan aplaus yang meriah pada Prof Syafiie. Aplausnya secara online ini.
Sure.
Baik,
terima kasih.
Terima kasih semuanya. Tetap sehat buat kita semua. Kita tutup dengan Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi
wabarakatuh. Saya ada 2 ini.
Iya.
Ini ada di pabrik karoseri. Nanti saya cerita deh kalau. Pulangnya baru malam ini nyampe rumah. Kira rasanya kita geser atau nanti kita bicarakan lagi ya Prof ya. Baik, izin saya close ya.
Oke. Sore nanti kemana Pak Arif?
Sore saya
petang malam nih.
Nggak ke Uber kayaknya, nggak Uber.
Nggak apa. Oke, tadi sudah
masih di luar. Masih di luar. Hari apa ya? Hari Kamis. Kalau Kamis justru Jumatnya libur, jadi mau malam Jumatan ya, Prof Syafiie ya. Jumat malam. Nanti kita diskusi di itu aja di grup aja di WA.
Oke. Boleh.
Mari Prof ya.